In section 1.6, we will work with limits again. In this case, because as the title has involving infinity, there's two cases really here. One is where you're taking the limit as you approach a particular numerical value, but the end result, the limit, is a version of infinity. Or in the second case, we are approaching infinity and we want to know how the function is behaving. So let's start off with problem number 13. So in problem 13, it says, what's the limit as x approaches -3 from the right side of x plus 2 over x plus 3? Now, -3 is not in the domain of this function. If you remember your college algebra and your pre-cal, you can probably tell me that there's an asymptote when x plus 3 is equal to 0, there's an asymptote at -3. Do you remember that from when you used to graph things, graph rational functions? So there's an asymptote there that we can't replace because we can't factor it out. We can't multiply by the least common multiple. There's no conjugate to multiply by. So we're going to have to use that sneak up on it attack. That's what I call it. Okay, so I'm saying sneak up on it. Okay. So we're just going to approach close to -3 and see what kind of answers we're getting and make an assumption. Okay, so I want a number to the right of -3. So if this is -3 on your number line, okay, I want a number to the right of -3 to kind of sneak up. Okay, so would you say -2.99 is to the right of -3? Okay, so we're going to substitute that in, and we're going to have -2.99 plus 2 over -2.99 plus 3. Now, in actuality, we can compute a number for this. Let me show you the general way, and then we'll compute a number. So -2.99 plus 2 is going to turn out actually to being -0.99. Would you agree? Okay, but actually all I care about is that it's some negative number. Okay, it's not close to 0, so it doesn't really matter what it is. It's actually close to -1. So if you have something that's like some numerical value that's not really, really, really tiny, then there's just the fact that it's a negative number is fine. However, on the bottom, okay, I've got 3 minus 2.99 if you read it backwards. So what do you get? Something like 0.01, a negative or a positive 0.01. Now let's put that over here. Put numbers over there. So over here, we would get a tiny positive. Now remember, this -2.99 is a number that we're getting close to -3, so we could even get closer. You know, we could do -2.999 plus 2 over -2.999 plus 3, which would get me a -0.999, which is even closer to -1. But here, I would have a 0.001, which is even smaller. Agreed? So remember, we're moving closer and closer and closer to -3, so we're getting closer and closer and closer. So this denominator is getting smaller and smaller and smaller as we go. And if you take any number and you divide it by a really small number like 0.001, it's going to blow up to be a very big number. Okay, so a negative divided by a positive is going to be a negative. And it's going to be a very large number, so we say it's negative infinity. This goes back to that 1.4 section where I said we're going to readdress this in chapter or section 1.6, and so here we are. So the limit, remember, we need a complete statement to look professional. Now that we are in calculus class. We are going to focus on our presentation as well as our accuracy. Okay, so let's do problem number 14 and say the limit as x approaches -3 from the left of x plus 2 over x plus 3 is, and I need a number to the left of -3. So the left of -3 would be right here. So I would need a number sort of like -3 point, I don't know, let's go really small. 0, 0, 0, 1 plus 2 over -3.00, 1, 2, 3, 1 plus 3. Okay, so in the numerator, I would have -1.0001 over, let me make this a little bit better, -0.0001. All right, now, but let's do this kind of generically, then we're going to go back and calculate up numbers. So -3.001 plus 2 is just some sort of a negative number. It's not a really tiny number, it's actually really close to -1. On the bottom, we have a tiny negative number. Okay, so if you take a negative and divide it by a negative, you end up with a positive. And any sort of a number, you know, that's you know, close to 1 or bigger, divided by a little tiny number, is still going to blow up. Dividing by this little tiny number is going to make it huge. So I've got a positive infinity. So let's look at these numbers right here. Okay, if you actually calculated up this number and you took this 0.99 that's negative and you divided it by 0.01, you would get 99. Agreed? And as you get closer, if you went down here and you had 0.999 divided by 0.0001, you would get 9,990. So 9,990. Let me try to get this a little bit better. 9,990. Okay, so do you see how as I'm getting closer, I'm getting a bigger and bigger number? So if you wrote on your answer to me that this was -99 or -9,990, well, you're aiming in the right direction, but it doesn't get to -99 or -9990 and stop. It just keeps getting more and more of a negative number that's farther and farther in the negative realm. So you can't use these numbers because I'm heading off and I keep getting closer and closer to -3. So this keeps getting, if you want to say, larger in the negative direction. So you cannot use these numbers. Okay, now you're welcome to use them if they help you decide what's going on, but don't give me those answers because I keep getting closer and closer and closer. I don't get to -9,990 and stop. Okay, likewise here, if you just divided this section right there and go 1.0001 and divided it by 0.0001, okay, you would get 10,001. So this is 10,001, which is a huge number, all right? So this tells you kind of which direction you're aiming in, but don't give me this numerical answer because that says that if you wrote that and then boxed it in, that would say I am getting to 10,001 exactly. That's where I'm aiming at, and I'm not going to get any higher. And that's not true. So the limit as x approaches -3 from the left, to make my complete statement, like I would want a complete sentence in English, looks like that. Now, let's talk about this. They don't ask you this question, but I think they should, and I might. All right. What if I had started with this question, and I had said, what's the limit as x approaches -3? And without a little plus or minus right here, I'm asking you for both sides of x plus 2 over x plus 3. What you would have to do in order to get full credit for your test and in order to justify your answer for your employer or your calculus teacher or your physics teacher if you were doing some sort of an analysis involving limits. So if you were going to actually present this information to someone else to read, if they ask you a two-sided limit, which is what this is, and you can't reduce this out to where you can substitute it in, you have to do these two parts. You would have to do, this is part A, and this would be part B. Doesn't matter which one you do which time. But you would have to do these two parts before you can answer this question. Does it make sense? So if I ask you a one-sided limit and it has an issue with the denominator where this is not in the domain and you can't reduce it, you do one test, you get one answer. If I ask you the other one-sided limit, you do one test, one answer. But if I ask you a two-sided limit, and if you cannot reduce this problem, and by problem I mean this that gives you 0 in the denominator, if you can't reduce that out somehow, then you have to give me the two parts. If you happen to know what the answer is, and you give me the answer either because you looked at the graph or because you just sort of instinctively know what the answer is, I'm not going to give you any credit at all, okay? Because you have to show me mathematically that you understand the process, right? So if you know the answer, fine. You know whether you're right or not before you turn it in. But you have to show me the two parts. You cannot use the picture or a guess to give me an answer, even if it's correct, without the work. Does that make sense? I hope you heard this. Because if you give me the correct answer without any algebraic work, it's going to be wrong. Okay? So what is the answer to this? If one side is going off to negative infinity and the other side is going off to positive infinity, I do not have a match. And so what you would say is it does not exist. Okay? So this would be the answer to the two-sided question. You would do both parts, see if there's a match, and decide. Now, sometimes students will tell me that if it has something that they can't reduce out, they're just going to always say does not exist because usually there's an asymptote there. But that's not always true, as this one that I'm getting ready to do is going to prove to you. All right. So the limit as x approaches 1 of 2 minus x over x minus 1 squared. Let's decide what this is going to be. All right, so 1 is not in this one's domain because I can't have 0 in the bottom. I can't reduce it out. I can't clean it up. I can't simplify it. So I'm going to pick a number. I'm going to pick, this is a two-sided limit, so I have to pick numbers on either side of 1. So I could pick, if I did the limit, since I'm two-sided, I'm going to do the limit as x approaches 1. Does not matter which one you do first. Let's do the left side. Okay, so the left side would be right here. Be sure that if you're doing the left side, you pick the left number. Okay, so let's try a number that's to the left. So would that be something like, oh, I don't know, 0.999? That would be to the left, pretty close, wouldn't it? So you would have 2 minus 0.999 over 0.999 minus 1 squared. Are we okay? All right. So in the top, I have a positive number. That's all you really need to tell me. And I'm perfectly fine if you just write, there's a positive number in the top. Okay? I'd even probably be okay if you went positive number, right? So I have some positive number in the top. And in the bottom, 0.999 minus 1 is a tiny negative number, okay? And then I'm going to square it, okay? So I still have a positive number on top. But a tiny negative squared, well, a negative squared is going to be positive, correct? So now you have an even tinier positive number, okay? And you'll even see me sometimes on my notes, all right, just for entertainment for me, all right, wee little tiny, just to make myself smile. Okay, so if you want to write me little notes like that, I am just fine. So I'm fine with tiny, tinier, even smaller, you know, whatever you want to call. So I've got a positive number divided by a positive number that's positive, and a number that's, you know, kind of get basically around 1 or something, divided by a little bitty tiny positive number is going to be a huge number. Okay, so this is going to be infinity. Everybody's okay? All right. I do need to talk to you about something about format in just a minute before we finish. Okay, so here's one part of it. All right, what's the limit as x approaches 1 from the right? So I would need a number to the right, so something like maybe 1.001, something like that. So I'd go 2 minus 1.001 over 1.001 minus 1 squared. Okay, so this top is still going to be some, you know, positive number. It's actually close to 1. But on the bottom, I'm going to have a tiny positive squared, right? So I've got a positive number of some sort divided by some little tiny, whatever you want to say, whatever makes you smile. Okay, there's not very many times in math you can smile. So if you can use some sort of cute word to get yourself to smile, I'm all over that. Little tiny positive, right? So a positive divided by a positive is a positive, and some random number divided by a little tiny positive is positive infinity. Okay, so here's this one's answer. Okay, so when we do this, did we get a match? We did. So both sides go off to positive infinity, so the answer for the two-sided limit is positive infinity. So everybody's okay? All right. Now, I do want to remind you, I think I've mentioned this in the past, okay, when you substitute the number in, you can drop this function limit off, but until you substitute a number in, you have to keep bringing along that limit, okay? So be sure that you keep up with that. We'll do that in a little bit. So let's do another one. They have a couple in here that I actually don't care for. So there's number 17 in there, I just skip it, right? 27 is another type, and it's the limit as x goes to infinity of x to the 4th minus 3x squared plus x over x cubed minus x plus 2. Now this is a rational function. We don't really want to graph this and see what this is, but as you're going off to infinity, you know, you used to have some sort of rational function that may have had asymptotes in it or not, and I don't know what this one actually looks like, but you know, we would have asymptotes like this where it would go off to 0 or something as you went off. So these were the horizontal asymptotes. So when they ask you about going off to infinity, they really are the asymptotes that we're talking about. We're talking about the horizontal ones. And in chapter 4, we're going to do a really intense revisit of how to graph these rational functions from the calculus point of view. And I'll make another big point of saying that these limits, as x goes to infinity or negative infinity, they're asking what's the behavior down here on the ends. And that has to do with both the end behavior and also the horizontal asymptotes, if they have any. Okay, now the best way, and the book does describe this, the best way to decide this without having to guess, okay, is if you have a rational function like this, and if you are going off to infinity. Now here you have a rational function, but you are not getting the limit as x goes to infinity, all right? So if you have these two things, you have a rational function, and your limit is as x goes to infinity, this is the technique you use. You look at the denominator, okay, you find the biggest powered term, which is this one, and you divide every term, top and bottom, by that. And for the purposes of your homework, I'm fine if you just sort of squeeze this in there, okay? So what you have, remember, you write the word limit down until you substitute something in, all right? So what you have is x to the fourth over x. Goodness, I thought I was doing pretty good here. Okay, so you have x. This computer program and I are not friends today, but I am going to persevere. Okay, x to the fourth over x cubed, okay, minus 3x squared over x cubed plus x over x cubed. X cubed over x cubed. And I'm just writing this bigger so that you can see it. Okay, now let's talk a little bit. Let me write this next part back. And let's reduce some of these, all right? So x cubed goes into x to the fourth x times. Agreed? Minus 3. And x squared over x cubed is over x. X over x cubed is 1 over x squared. X cubed over x cubed is 1 minus 1 over x squared plus 2 over x cubed. Okay? Now think, you've got this huge number, all right? So x to infinity is a huge number. I mean, I'm talking a billion, you know, maybe as low as 1,000 or something like that. But you're not looking at 2s and 3s and 4s and 10s. You're looking at thousands. Okay, so if you have some value, let's talk about this. If you have a 3 divided by 1,000 or 1,000,000 or 1,000,000,000, 3 divided by a huge number is awfully close to 0. 1 divided by a huge number squared, right? So if this was like 1,000,000 squared, this would be going off to 0. 1 over x squared is 0. 2 over x cubed is 0, right? Because if you have 3, let's say we're going to use 1,000,000. 3 over 1,000,000 is close to 0. 1 over 1,000,000 squared is even closer to 0, right? Okay, so that's what we're doing here. So this leaves me the limit as x goes to infinity of x over 1. You with me? Okay, so what happens when you substitute infinity in there? You have infinity over to 1, which is infinity. So the limit as x goes to infinity of x to the fourth minus 3x squared plus x over x cubed minus x plus 2 is infinity. You okay? All right. Now, let's look at this a minute. If you get tired of writing these limits, these right here. Okay. If you get tired of writing the limits and you have to have this x goes to infinity and you have to take the limit of something, you can't just write limit and have this be blank, okay? So it's like saying, what's the square root of a blank? Well, that makes no sense, right? So what's the limit? It has to be the limit of something. and you have to be approaching something, so you have to have all these pieces and you have to keep writing them. And if you drop this off, I'll be taking off points, and you may still have the right answer, but I'm going to take off points because you're not approaching the problem correctly. You actually changed it and then changed it back, so you can't do that. Okay, so I'm going to make one up a little bit. So what if you had the limit of x goes to negative infinity of let's say 2x to the fifth, I'm making this up as I go, minus 3x squared plus 4x over, let's see, x squared plus 3x plus 5. Okay, so here you have a rational function. You're taking the derivative. You're taking the limit as x goes to negative infinity. And so the way I'm going to do that is to look at the denominator. You always start with the denominator. You find the biggest power term, which is x squared. You divide everybody by it, because essentially you're dividing the top and the bottom by x squared, so you're dividing by 1. And you would have the limit as x goes to negative infinity of, let's go ahead and reduce it. We don't save ourselves a step. So we'd have 2, everybody with me, and x to the fifth over x squared is x cubed. Okay, minus 3 times 1, right? Plus 4 over x. And then you'd have 1 plus 3 over x. It's not going to let me do it. Let's try this again. All right, plus 3 over x plus 5 over x squared. Now remember, x is going off to some really big negative number, so it might be like negative 10,000. Let's just say, let's say this is what we're going to do. So 4, okay, over a negative 10,000 is going to be really close to 0. Now it's maybe the negative side of 0, but it's still going to be close to 0. 5 over a negative 10,000 squared is going to be even closer to 0. 3 over negative 10,000 is close to 0. Everybody with me so far? So this gives you the limit as x goes to negative infinity of 2x cubed minus 3 over 1. Well, 2x cubed minus 3 over 1 is 2x cubed, so we have 2 times negative infinity cubed minus 3. Are you okay with that? Now, let's think about this negative 10,000 cubed. If you double it, right, okay, let's start over. So you have negative infinity cubed. It's still going to be negative. Infinity cubed is even, this is not a good word, but huger, okay? So negative infinity cubed is even a more negative number. Times 2 is even more negative, and subtracting 3 is even more negative, so you're going to end up with negative infinity. We don't write negative infinity cubed or negative infinity, we're aiming just farther down the negative infinity direction, and so that's good enough to say I am heading in that direction. There is not infinity squared, infinity cubed, 2 times infinity or anything. It's just I'm heading in this direction. And even if this had been a plus 3 or something, we're still off down the negative infinity direction, and so that would be what we would write. So let's go on and do a couple more problems way through this section. Okay. They have a problem that I don't like either. I think this is sort of like mean. Okay, so what's the limit as x goes to infinity of cosine x? Now remember, we're supposed to be approaching a number like 4 or 5 or -10 or something like that. My poor dog. Okay, so they kind of lie a little bit and say, okay, so negative infinity here is not really a number, but it's a direction. So we'll kind of go along with the fact that it's a direction instead of a number. But cosine, you remember what cosine looks like? It looks kind of like this, right? So what is cosine doing as you go farther and farther this direction? Does it ever start hovering in a particular direction or hover near a particular number? No, it just keeps going through this same oscillation forever, right? So is there a limit of cosine as you get farther and farther to the right? Does it approach a value or approach a particular direction? No. So this is just, it does not exist. I'm not approaching a value. And I'm not approaching a direction, so this would be my answer. I actually don't like this problem. Okay, but it is what it is. So let's look at 31. If you have the limit as x goes to infinity of x minus the square root of x, literally what you have is infinity minus the square root of infinity. All right. Well, you're already aiming to infinity, which is a you're aiming up now, remember, right? Because this is y, you're getting y values. So you're aiming up toward infinity, and then you're subtracting whatever the square root of that is. Well, a huge number like 10 million divided by, minus the square root of 10 million is still a huge number. So everything's relative. This is infinity. Okay? So if you look at 33, and I'm not a big fan of these problems because there's no math to this. You just sort of have to understand it. So I consider these kind of tacky questions. All right, but I'm showing them to you so that you don't try them and you won't be upset, too much at home trying to figure out what technique you're supposed to be using, because these are just kind of reason it out problems. So a negative infinity to the fourth is going to be a positive infinity. And it's actually, okay, a positive infinity to the fourth, but we don't ever say that. And a negative to the fifth, since it's an odd power, is going to be this. So who's going to win, right? If you've got a positive huge number to the fourth and that a huge number to the fifth, subtracting it, the negative infinity is going to overpower the positive one, and this would be your answer. But I am more interested in, can you use the right technique at the right time? There's times when and it's coming up in the next chapter, there's times when I ask you questions that I consider kind of, if you understand it, you get an answer really fast, and if you don't understand it, it takes you forever to get an answer. But that comes up really in the next chapter. Though, we could talk about some now. For instance, if you have, what's the limit as x approaches, I would think this one would be legal. Let's see, pi over 2 from the right for cosecant x, right? So here's sine. Okay, cosecant sits right on it at its peaks and valleys. This is pi. And it has an asymptote right here. And this repeats every 2 pi, right? So the red is cosecant, the blue is sine. So what is y approaching on the cosecant curve as x gets close to pi over 2? Well, as x gets close to pi over 2 from the right, it's approaching 1. Remember, they touch at 1. From the left, it's approaching 1. So this is 1. Whether it's coming from the right or the left, if it had been a two-sided limit, because of what I said, it's still 1, right? But what if I had said, what's the limit as x approaches pi from the right. Okay, so as x approaches pi from the right side of it, this is going off to negative infinity. What's the limit as x approaches pi from the left? Okay, so here's pi, and as you approach it from the left, it's heading off to positive infinity. Okay. What then would be the answer for x approaching pi from both sides for cosecant? Well, it does not exist because there's not a match. So, you should be prepared for simple questions like this. And for the trig ones, okay, for the trig ones, I am just fine if you draw the figure. Okay, so if you drew the figure here and use that question or this figure to answer the questions, I am fine with that on trig. You cannot use a picture to answer the ones that are algebra. Okay, those you have to use algebraic methods to get an answer, but you can do this for a trig one, all right? And so these are the versions that I would ask, okay, where it has up here what's going on with cosine, right? I wouldn't ask that kind of a question. I would ask this sort of a question, or what's the limit as x approaches pi over 2 from the left of tangent? Okay, well, tangent looks like this. Here's pi over 2. Okay, as it approaches pi over 2 from the left side of pi over 2, it's racing off to positive infinity. Okay, you would need to draw another period to say what's it doing from the left side. And so it would be going, from the right side. Sorry, we already did left side. From the right side of pi over 2, it would be negative infinity. All right, so those I think would be, well, I don't think that is more my style. All right, and you can, like I said, draw the figure for the trig ones. You cannot draw the figure from here and get it off of your calculator. I want to see the math. Everybody understand? Okay, so that's the end of section 1.6.